Hi, welcome back to Mathematical Logic. In this lecture, we'll talk about first-order theories. So a few lectures ago, we talked about first-order language. So suppose we have a first-order language L, and so a first-order theory T consists of a language L together with collections of first-order sentences, which are constructed using the symbols of L, and we'll refer to these sentences as axioms of T. And so essentially these axioms are first order sentences that we just assume to be true. So that's going to be our first order theory. A model M of T of this theory is basically an interpretation of L that also satisfies the axioms of T. So it satisfies the first order language as well as the axioms that we impose on T. So there's actually many important mathematical structures that are actually models of some chosen first order theory. We're going to cover some of these structures in this lecture. So again, first order theory is basically you take first order logic that we've been talking about last few lectures, and then we add some axioms on top of it. And in a lot of areas of mathematics, you have this kind of a pattern where you take logic and then you take some axioms and then you add to, and then you get different kind of field of mathematics. For example, number theory, geometry, group theory, topology, even linear algebra or analysis. All these usually start out with some axioms and then you build on top of those axioms. Okay, so let's consider the first order language consisting of a predicate with two arguments. So this is just a relation of two arguments of x, y, and this relation is essentially the less than equal to relation. Suppose also that this predicate satisfies the following axioms. For x of xx, so this is reflexive. For x, for all y, for all z, all xy, and all yz implies all xz. So this is the transitive property of this relation. So if for example, if x is less than or equal to y and y is less than or equal to z, then certainly x is less than or equal to z. So this is a transitive property. For x for all y of xy and all yx means that x and y is the same. So this is the anti-symmetric property. If x is less than or equal to y and y is less than or equal to x, that means that they must be the same. And then for all x for all y, all xy, or all yx. So given to any two elements, either x is less than or equal to y or y is less than or equal to x. And so this is, we see that this is the less than or equal to relation is an example that we've seen already in math. And so it turns out that there's actually many sets that satisfy this theory. And so this theory is also called the theory of linear orderings. And a set satisfying only the first three axioms, the first three, A1 to A3, is called a weak partial order. And then if you also satisfies A4, then you call that a total order. So for example, let T be a theory of linear orderings. If we take the set the real numbers and you put on this less than or equal to relation, binary relation, then this is certainly a model that satisfies the axioms for this theory, the theory of linear orderings. And this relation actually forms a total order on the set of all real numbers. Given any two numbers, you can always compare them, essentially. Partial and total order is also important in programming. So for those who are CS majors, especially when you have like sorting algorithm, sorting out an array, for example, usually implies finding some kind of total order on the elements. So for example, you have a set of prices. We want to order objects based on price. But sometimes you can't always put an order on objects, and so but even in those cases we still can sort if we do have some kind of a weak partial order. And so again, this is beyond the scope of this class, but in computer science, when you talk about regular versus stable sorts or topological sorts, some of these have to do with this partial order. Okay, let the language L. So here's another example of a theory. So suppose you have a predicate letter A1, 2, and also a function letter, and an individual constant A1. And we're going to denote the domain, we call it G. So to kind of fit this with common notation in group theory, we're gonna, instead of saying A12 here, this binary relation is going to be equality, and this function f is going to be just some kind of multiplication or any kind of operator. It doesn't have to be multiplication, but some kind of operation between two elements. And then A1, we call that the identity. So here are the axioms of this theory. So for all x1 for x2, x1 times x2 is an element of G. This is also known as the closure of the prop of this operation. That means that if you take two elements that are in the domain and you operate them by applying this operation, the answer should also be an element of this. So this is called closure. So this is the first axiom. And then for all x1, x2, x3, this operation is associative. That means if I group them this way and then multiply, the same thing as grouping them this way and multiply. And then for x1, the identity basically doesn't change the answer when you multiply. So e times x1 is x1 for all x1. This is the e is called the identity. This individual constant here. So we need to have at least one constant, and that constant is the identity. And for all x1, there's an x2, so that when you multiply them, you get the identity. So x2 is called the inverse of x1, and sometimes we denote x2 as the x1 inverse. So these four properties are the one. If you have a set that has an operation and satisfying these properties, we call that set a group. Technically, there's actually a few other axioms that has to do with equality axioms, but I'll list them here. But really, these for the most part, these are very obvious, right? If we have equality, it's reflexive. Anything is equal to itself. Symmetric. If something is equal to something else, then certainly is reversing it is also still true. Transitivity of equality. If x1 is equal to x2, x2 is equal to x3, then certainly x1 is equal to x3. And finally, you can substitute. If x2 is equal to x3, then you can substitute x2 for x3 and vice versa. And so and you can flip it. And so these are obvious. Usually we don't have to check these. We typically check just the first four, and then if it satisfies these four, then it's a group. These are kind of obvious based on our equality predicate. So okay, so a theory. This theory is called elementary group theory. Elementary is actually just another term for first order. So this is a group theory that is first order group theory. A model for this theory is called a group. So this is actually a very important idea in mathematics. And a group is abelian if this statement is also true for all x1, x2. If you multiply, the order doesn't matter. So that means that the operation is commutative. Okay, so it turns out this structure is actually very useful in math, but also there's many similar structures that are variants of the structures: groups, vector spaces, rings, fields, etc. So and so all these examples actually come from some kind of a first order that has a set of axioms that you get these structures from. And so this is certainly a very important example of first order theory. So we're gonna explore this in more detail so we really understand this one example, so that when you see other example built on top of first order logic, then it will make a little more sense. So let's do this in more detail. So let's see some examples of a group. So if G is a set of all integers and the operation is addition, this is a group. So the first axiom is closure. That's certainly true. You have two integers, you add them, you get another integer. Obviously, addition is associative. The identity is 0, because if you add anything to 0, you get itself again. So that's the axiom 3. And then we need to have inverses. So for any x1, let x2 be negative x1. So remember when we talked about proving mathematical proofs, to prove the existence of something, we just produce that something. So given any x1, if you negate it, then that's the inverse, because if I add something to it, negative, I get 0. So that's A4. So which the four properties are clearly satisfied. So this is a group. This group is also abelian, because addition is abelian. If you change the order of addition, it's the same. Another example that's similar to this one is if you take the real numbers and then use addition, that's also a group. Here's a non-example. What if you have G is non-negative integers, set of non-negative integers, and then this operation is addition also. So again, the first few properties are obvious. You can check those, and then this is the identity. It's just like before. Everything's the same as before, basically, except that there's no inverses. Given an element, there's no if that element is non-zero, there's no inverse. For example, if you have x1 is 1, there's no x2 so that when you add it to x1, you get 0. And so this doesn't satisfy A4, so therefore this is not a group. Again, notice that -1, right, is not in G, therefore the inverse does not exist, and A4 is not satisfied. Rational numbers and multiplication is also another example of a group. So again, multiplying into rational non-zero. By the way, this is non-zero rational numbers. Multiplication of non-zero rational numbers give you another non-zero rational number. So that's obvious. Multiplication is associative. The identity is 1. Notice it's 1, not 0 in this case, because when you multiply by 1, that doesn't change the answer. For all x1, 1 times x1 is x1. And finally, the fourth axiom is finding inverses. Given any rational number that's non-zero, the inverse is basically just you flip the fraction, because when you multiply them, you get 1, which is the identity. So given any element, this is its inverse. Yeah, so in your homework, you get to kind of do some examples of some of these proving certain things are groups. So you want to kind of get used to these four axioms and how to prove them. So that's another example. Here's another one. If you take the set of invertible n by n matrices with real entries, and the operation is matrix multiplication, that again, if you've done linear algebra or even just basic pre-calc, you've done some matrices. So here's the identity element. If you multiply this with anything, you get itself again. And certainly A4 is satisfied because we're only including invertible matrices. There's actually matrices that are not invertible, where there's no inverse. But so if you look at only the invertible matrices, that also forms a group. This group is not Abelian. It's easy to find two matrices that multiply, that if you switch the order, they're not the same. Here's another example. If you have this equilateral triangle, and we take a look at the group of symmetries of this triangle. In other words, you just rotate or reflect so that this triangle is preserved. And then so the symmetries are the elements, and then the operation is basic function composition. If you have two functions, you just compose them. So the identity is the symmetry that doesn't do anything. If I don't do anything, then that certainly is the identity. Here's another element that is not the trivial element, which is if I take this and I rotate it by 120 degrees clockwise, notice that this triangle is preserved. The triangle becomes the triangle again. So that's an element of G. That's a symmetry. By the way, in terms of what happened to the vertices, right? A function is determined by what happened to these vertices. So this rotation is it's going to take 1 to 2, right? 1 go to 2. That's the rotation. 2 go to 3, and 3 go back to 1. So that's that rotation. So you can denote this group element as what happened to the vertices. So here's some more elements. If you take R, the rotation, and multiply by itself, you get R squared, which is basically a rotation of 240 degrees against clockwise around the center. So 1 goes to 3, 2 goes to 1, and then 3 goes to 2. So that's that element. If I rotate this 3 times, if I multiply R 3 times, I get R cubed, which is back to the identity. If I rotate this that R 3 times, then I get a rotation of 360, which doesn't do anything. So that's the identity. 1 goes to 1, 2 goes to 2, 3 goes to 3. So that's 3 elements that we just generated. Here's another element of this group. We have reflection. Reflection certainly preserves the triangle. So for example, if I 2 stay the way it is, 3 goes to 1, 1 goes to 3. So I reflect along this vertical line. So that's a reflection. And then what if I take two things and I multiply them? For example, S, the rotation, and S is the reflection, and R is that rotation. So again, it doesn't matter, but when we do function composition, the convention is to do right to left. I do S first, and then I do R. That's how we usually write our function notation. And so, for example, if I reflect and then rotate, 1 will goes to 1, because again, I reflect over to 3, and then I rotate back. 2, 2 reflection stays there, and then rotating will go to 3, and then finally 3 reflection goes to 1, rotating goes to 2. So if I compose these 2 elements, then the answer is this, which is actually a reflection around this line right here. And so composing a rotation with a reflection gives you another reflection. So if you do all this out and multiply different ways, it turns out that you get 6 elements. There are 6 elements of this symmetric group, right? 3 rotation and then 3 reflections. And then yeah, so that's how you get those elements. And finally, here's a kind of a famous group, which is the Rubik's Cube group. Here's a Rubik's Cube. The moves performed on Rubik's Cube is that form a group. This group is a set of all moves. So if you have 2 moves, the multiplication of the 2 moves basically is the move that basically is concatenation of doing the first move and then followed by the second move. So certainly if I have 2 moves and I do 1 move and then do another move, then the result is another move. So that's you have closure, and then the identity is the move that doesn't do anything. Every move has an inverse clearly, because whatever I do, I can always undo it. And so this group is huge, has a lot of elements. It has this many elements, turns out. And so, for example, if you have the Rubik's Cube that you buy, and you put for every different unique position of the Rubik's Cube, you have its own Rubik's Cube, and you place them on the Earth. And then if I have then this number of Rubik's Cube placed on the Earth will cover the entire Earth 300 times, right? So this group is huge. But I guess one thing I would say is that there's a proof that has recently proven using computer that we can actually solve a Rubik's Cube starting with any configuration, and you can do it in 20 moves or less. So any Rubik's Cube can be solved in 20 moves or less. So the number 20 is also called God's number. And also more recently, a couple of years ago, there's an algorithm that's done using neural networks, which is deep learning, machine learning. I use neural networks to actually solve this Rubik's Cube. I think it uses reinforcement learning and a search algorithm called Monte Carlo tree search. And in fact, that's a similar algorithm is actually used for computers to be really good at playing the game Go. For a long time, Go was thought to be far away from being played well on a computer. But a few years ago, 2016, Google has an algorithm that was actually able to beat the best human player, and so that was a big surprise. Yeah, so it's just a couple of interesting facts. Okay, I think that's it for this lecture. Thanks for watching.